Okay, here's the follow-up to March 27th for Chem 343. Okay, first question is, in the E2 reaction, does the alpha carbon need to be a chiral center? And the answer is no, it does not need to be. Okay, so this has to do with trying to figure out what you need to go into the box to make a certain product. If the product is like this, or like this, then no, the alpha carbon does not need to be a chiral center. If the product is like this, the alpha carbon does not need to be a chiral center. But if the product is like this, then both the alpha carbon and beta carbon need to both be chiral centers. The difference is, in the case of these two molecules, they don't have diastereomers. It doesn't matter. This molecule is the same as this. This molecule completely separate. This molecule also doesn't have a diastereomer because the 6-membered ring is too small to have a trans double bond. So in these cases right here, the alpha carbon and the beta carbon don't need to be chiral centers. And so here, this is a good answer. Or this, either one. In this case right here, this is the only good answer that you'll have. Mainly because this would give SN2 products. In this case right here, they don't have to both be chiral centers, but you do have to worry about the anticoplanar rule because the alpha carbon and beta carbon are part of the same ring. So this would be acceptable. Or if you put your alpha carbon over here, since the bromine's a wedge, the hydrogen has to be a dash. So this would be an acceptable answer. Or this would be an acceptable answer as well. Okay. So lots of possibilities here. In each of these cases, the alpha carbon and beta carbon aren't both chiral centers except for this last case right here. Okay, but there are lots of possible answers. This one right here, though, they both must be chiral centers. Let me explain that. There are two possibilities for alpha carbons. Because you can have your alpha carbon here, or you can have your alpha carbon here. Okay? Now, the thing is, the problem with this one right here is they are not both chiral centers. There are two hydrogens here. And so when you're to treat this molecule with a base, It doesn't matter what the stereochemistry of this alpha carbon is, if it's R or S, it doesn't matter because this beta carbon here isn't a chiral center. You end up with the product that you want, plus the diastereomer you don't want, because there are two hydrogens here. One gives one, the other one gives the other. And in the synthesis problem, the idea is to make the target product as cleanly as you can without any other products, if possible. This molecule right here, both the alpha carbon and the beta carbon are both chiral centers. That means that there are two possibilities of diastereomers. If you get your stereochemistry right, you'll just get one of them. So if you treat this molecule with sodium methoxide, notice the hydrogen and bromine aren't in the anticoplanar position, so this needs to be redrawn. Like so. So now they're anticoplanar. When you do the elimination, the ethyl group and the methyl group are both wedges, so they end up cis to each other. The phenyl group is a dash, so that ends up trans to the ethyl group. So this is the product. If used its enantiomer, what that means is you switch both the chiral centers. So if you switch both chiral centers, and you redraw the anticoplanar, the H and the Br anticoplanar, basically have this. Again, the ethyl and the methyl are cis to each other because they're both dashes. Phenyl is a wedge, so that's trans to the dash ethyl. And you get the same product. So it doesn't matter which enantiomer you use, you get the same diastereomer. Now if you start with the other diastereomer, that, when we draw the H and the Br anticoplanar to each other, get that. Now both the ethyl group and the phenyl group are both dashes. So they end up cis to each other. The methyl group being a wedge ends up trans to the ethyl group. You can draw it as this enantiomer or the other enantiomer. And you get the same result. And the one that we want, the original problem, is the phenyl and the ethyl cis to each other. And so this would be the correct answer for that problem. Either of those would work. Okay. Now, problem set 20, 2D. Okay, problem set 22D is a synthesis question. Synthesize the following from starting materials containing 7 carbons or less, and carbon containing starting materials cannot be ionic. Okay. And 2D is looking at this molecule right here. Okay. Now, it is awfully tempting to think of the alkyne reduction as a first step backwards, because that allows you to put an alkyne anywhere between where you have 2 CH2s Let me number this, just make sure I did it right. Yep, did it right. Although technically this works. Don't do it. Don't. Because what you have done is you made the problem harder. You started out with really just one functional group. Don't have to worry about the benzene ring. The benzene ring is very unreactive and will survive a lot of different conditions. Other ones, not so much. Other functional groups. Here we really have just the one reactive functional group, the ether. If we go backwards a step from hydrogen and palladium, we get an alkyne. Now we have two functional groups to worry about, and we're worried about whether one's going to affect the other. So please, 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 only use this for alkanes. If you don't have, okay, if you have any other functional group, focus on that functional group. I'm trying to save you guys a lot of trouble later on. Actually, no, I'm trying to save myself a lot of trouble later on because I'm the one that has to grade these things. So, we have ourselves an ether. Ethers are made by an SN2 reaction. And there are two carbon-oxygen bonds. So if we break it between the carbon-oxygen drawn between, and let me just label this carbon, the oxygen is 7, that carbon is 8. If we break the 6-7 bond, then our starting materials are this. The oxygen side gets an O minus because you're trying to do an SN2 reaction, because that's what makes ethers are SN2 reactions. The carbon side gets a leaving group. Okay? So if we do that, we have this molecule on the left has 8 carbons total, so we have to make it. The molecule on the right has 7 carbons, but it's ionic, so we have to make that. Well, this one's pretty straightforward to make. If you're going to make an alkoxide, you basically just add sodium hydride to an alcohol. Now, the mechanism of this reaction is simple. Whenever you see a sodium, get rid of it. Sodium hydride is really H-. There are so many people that try to incorporate the sodium into the products, and they end up getting it wrong each and every time. So just get rid of it, the sodium, and replace it with a negative charge. And all that mechanism is an acid-base reaction. H- steals that H, goes there, and you get that O-. That's the mechanism. There's nothing magical about it. It's just acid-base. Now, the resulting alcohol has 7 carbons and is non-ionic, so you don't have to make that. Check. This molecule you still have to make. The functional group is a bromide. Well, we have different ways of making bromides. We could make this bromide from an alcohol, and now we have different ways of making bromides. PBr3 is a very good way of making bromides because it doesn't do a lot of side reactions like HBr can. If you do HBr here in this example, it's perfectly acceptable. And that can make the alcohol. Now this alcohol still has 8 carbons. Well, the alcohol, one way of making the alcohol is by forming an alkene. Now, where the OH goes on that alkene is it goes on the anti-Markovnikov side. It goes on the less substituted side. So the conditions necessary for that are hydroboration. The key is what you want to do in the pattern of these synthesis problems is get back stepwise back to the alkene. Then you can go to the alkyne, and the alkyne is what you want to get back to because that is where we make the carbon-carbon bond. That's how we get under these 7 carbon, these limits of the number of carbons. So we have our alkene right here. To make an alkene from an alkyne, we use H2 and Lindlar's. H2 and Lindlar specializes in making cis alkenes. It's also the one that you go to make the terminal alkenes, where the alkene is at the end. Notice this is neither cis nor trans. It's a terminal alkene. Terminal alkenes come from terminal alkynes. And that terminal alkyne comes from an SN2 reaction where you make the bond next to the alkyne. So you make the 4-5 bond. You're making this bond right there. So carbon 4 gets the leaving group, bromine. Carbon 5 gets a lone pair and negative charge. Look how much similar that is to the ether breakdown. Same concepts. Do a quick double check. make sure the carbon with the leaving group is primary. That way, you're going to end up with the SN2 reaction and not the E2. So this has 1, 2, 3, 4, 5, 6 carbons. It's non-ionic. You don't have to make it. Check. Can stop here. This alkyne, the protonated alkyne, has 2 carbons, but it's ionic, so you do need to make that. And the way we make deprotonated alkynes is NaNH2. The mechanism for this is very similar to the mechanism for the sodium hydride, except your base, NaNH2, is just NH2 minus. And it's just an acid-base reaction. Okay? But that gets to this molecule right here. This molecule is acetylene. It only has 2 carbons and it's uncharged. It's non-ionic, so you don't have to make it. Check. You're finished. You've made that compound. Now, that's if we've made the break at the 6-7 bond. What instead we made the break at the 7-8 bond? Well, in that case, carbon, the oxygen ends up over here. That's the side of the O minus. In that case, carbon 8 gets a Br. Now this compound has 7 carbons or less, so that's fine. Don't have to make it. Check. This compound right here is an alkoxide. Where we make alkoxide is sodium hydride. That comes from that alcohol. Notice this alcohol right here is the same alcohol that we had right here. And so for the rest, it's just the same process over again. Now looking back at this, there's actually, you can make this synthesis a little shorter. This is perfectly acceptable the way you have it. But notice we have a bromine in the anti-Markovnikov position. We can install that bromine directly in that position. It's a shortcut. But you can go directly from this alkene right to this bromide by using HBr and peroxides, and you get the same result. Just notice that. But anyways, lots of different ways of doing this. Lots of right answers. Always many more wrong ones. Okay. That's 2D. Problems at 21-1E. Okay, problem set 21, 1E. Okay. Okay. Problem set 21, 1E is it's a synthesis problem. The key to this synthesis problem is realizing when you see a direct way and when you don't. Here, there's not an obvious way to go from the starting material to the product. So forget about the starting material, focus on the product. Product has an alcohol. We make alcohols from alkenes. Now that alkene can come from one of two different ways. It can come from like this, in which case the alkene would look like this. Let's put this in red. Or the alkene can be located over here. Either of these are possibilities. So now it's time to judge which one's the better one. And that's by looking at the carbons. If you look here on the blue one, carbon 1 and carbon 2 are pretty much identical. They are both secondary carbons. That means you're not going to have a chance at selectivity. Any of our methods is going to add an OH to carbon 1, or it's going to add it to carbon 2. And you're going to get a mixture of constitutional isomers. There's no way around it, making this a poor choice. But if we take a look at the red one, carbon 1 is secondary, carbon 2 is tertiary. There's a definite differentiation point, so you can add the OH to selectively to either carbon 1 or carbon 2 depending on what reaction you choose. And that's what we want. So therefore the blue route is not good. The red route is the one that we want. And we want the OH to be on the less substituted carbon. So of our three ways of adding oxygens, adding water across an alkene, we want to use hydroboration because that is anti-Markovnikov. We'll add the OH to the less substituted side. It also has the added benefit of being a syn addition, meaning if the OH is added as a wedge, the hydrogen is added as a wedge. That's just what we want. So now we have our alkene. We want to take a look. Is there an easy way of taking our starting alkene to our product? And if you see a way, go for it. It's not an obvious way. So forget about this. Focus on our starting material. Sorry, not the starting material. Focus on our product. How do we make alkenes? Specifically, how do we make tri-substituted alkenes? Tri-substituted alkenes come from elimination reactions. They do not come from alkynes, mainly because the alkyne that you would need to make that alkene looks like this, and you'd have a 5-bonded carbon. So, don't use alkynes to make tri-substituted alkenes. Also, you really shouldn't use alkynes to make any sort of cyclic alkene either, because of the ring strain involved in the triple bond in a ring. So the types of alkenes you make from alkynes are either cis, they're either trans, cis, or monosubstituted alkenes. That's it. So, you got the elimination. Your elimination, your leaving group, can either be on that carbon or they can be on that carbon. This is where we can look at our starting material again, and let's actually orientate it a little bit differently. We see that here is a match. There, problematic. But there to there is perfectly acceptable. And so now it's a matter of figuring out what we want as our leaving group. Lots of choices here. If you have Br as a leaving group, then the reaction that you would do to create the alkene on the right is an elimination. And the reaction to make the bromide, well, we want the Br to be on the more substituted carbon, so we use HBr. So that is one possibility. HBr followed by a strong base to give the E2, followed by hydroboration. Or if you had an alcohol, you could have done an E1 elimination with sulfuric acid, and then to install that alcohol, you can do oxymercuration, followed by demercuration. Or, since you're dealing with a tertiary carbon, you're not going to have to really worry about rearrangements. You can use catalytic H2, SO4, and water. So that's another option. There is a third option, and it's related to this route right here. So basically what you're doing is you're doing an E1 reaction followed by, you're doing a reverse E1 reaction followed by an E1 reaction to give you the alkene. Well, if you just treat this alkene with concentrated sulfuric acid, it would end up giving you that product. The way this reaction works is it starts out the same as anything as the addition reaction to alkenes, or the reverse E1. But in this case right here, you don't have water as a nucleophile to add to it. You don't have any nucleophiles at all. And when you have a carbocation without a nucleophile present, well, that carbocation, you can have a weak base, take the H off, and do the second step of the E1 reaction. Like so. So that's another possibility. Again, lots of right answers. And there's just not enough time to write them all on an answer key. Okay. Palms at 21, 8C. Okay. Okay. So, it's another predict the product question. Taking an alcohol to an alkene. Your first thought might be, well, an alcohol to an alkene. Let's just use sulfuric acid and do an E1 reaction. The problem with that is, if you do that, you get the product that you want, but the E1 reaction has no stereochemical control. Meaning if you have the possibility of diastereomers, you'll get them both. If you're wanting just one diastereomer, the reaction you need to use is an E2 because of the anticoplanar rule. And earlier we talked about the importance of when using the anti-E2 reaction that the alpha carbon and the beta carbon must be chiral centers if you're going to create one diastereomer when there are multiple diastereomers possible. So in this case, we want to put the leaving group here in order to have both the alpha carbon and beta carbon as both chiral centers. Now if we take a look at our original molecule, we're starting out with this alcohol right here. We have control over this chiral center right here. We can make this chiral center an R or an S when we change it into a leaving group, because that's what PBr3 and tosyl chloride specialize in. PBr3 inverts the chiral center, tosyl chloride retains it. What we don't have control over is this chiral center right there on the beta carbon. So we are going to go ahead and fix that as a dash. That means this hydrogen right here is a wedge. Now I drew the lines exactly as they are. It's up above. Only thing I didn't draw in was a double bond. Then I changed the methyl group to a dash to match this stereochemistry. That means the hydrogen is a wedge. Well, for the anticoplanar rule, if the hydrogen is a wedge, then your leaving group should be a dash. Now, to go from here to there, we actually need to invert the alpha carbon. The one that inverts the alpha carbon is PBr3. So PBr3 is going to do is change this OH into a bromine, inverting the alpha carbon. Now with the hydrogen and bromine anti-coplanar to each other, we do the elimination. If necessary, you can redraw this molecule to double check. You get this. The methyls are both dashes, so they end up cis to each other. And then you just need some base, strong base to do the elimination, like sodium methoxide or sodium hydroxide, something like that. You don't want it to be a bulky base because you don't want the double bond to appear on the less substituted side. So here's the answer. Okay. Problem set 20, 2C. Problem set 20, 2C. Okay. Need to make this molecule from compounds 7 carbons or less. It's a synthesis problem. And they have to be non-ionic. Here, our functional groups is a benzene ring. We don't have a way of making a benzene ring, so therefore that has to stay put. The rest of the molecule is an alkane. Alkanes, well, they come from alkenes or alkynes. If we're going to make a molecule from smaller molecules, it's best to think of this alkane as coming directly from an alkyne. Now, this is a good reason to use H2 and play on carbon in this last step, because there are no other functional groups. Don't worry about benzene. Benzene doesn't react with anything. It's there to make the problem a little bit more complicated, and we'll talk about how it does in just a moment. But you can make the alkyne between any carbons that are between any two CH2s that are adjacent to each other. You can make it here, 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 or there. Lots of possibilities. But let's look at our limits right here. 7 carbons or less. Well, we don't have a way of making benzene rings, so this has to be on it. So let's try to make make the alkyne as close to that as we can. Let's put it right here. Put that alkyne right there. Let me number. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 5, 6. We get this right here. And this molecule has 12 carbons. We need to make that. So let's try splitting it. if we split it over here, when we make alkynes from an SN2 reaction, well, actually it says 7 carbons or less. So this piece right here is 6 carbons. This piece right here is 6 carbons. So it seems kind of logical. We split it right there. So we split it right there. One, two, three, 4, 5, 6. When we do this split, the alkyne side gets a lone pair and a negative charge. The other carbon side gets a bromine. And now we've run into an issue. The way we make alkynes is by an SN2 reaction. And you cannot do an SN2 on this bromide because that carbon right there is sp2. So as a result, this synthesis does not pan out. So we can't put the alkyne between carbons 5 and 6 because of this reason. Because you can't make this compound. For a very similar reason, you can't make this compound either, and it has 8 carbons. So therefore 5 and 6 is a bad choice to make the alkyne. So let's go one more carbon over. Let's make the alkyne between carbons 4 and 5. With H2 and palladium and carbon. And then we can make this alkyne by an SN2 reaction. We're going to make the split here because this side has 5 carbons, and that makes this side have 7 carbons. Both sides are below our carbon limit. Carbon 5 gets a lone pair and a negative charge. Carbon 6 gets a bromide. And unlike earlier, this bromide is attached to an sp3 carbon. It's also primary, so it's capable of doing SN2. This molecule, benzyl bromide, has 7 carbons or less and is non-ionic. We don't have to make it. Check. The deprotonated alkyne, the acetylide, has 5 carbons, but it's ionic. We have to make that. We make that by deprotonating a terminal alkyne, NaNH2. Okay, and you get that. And so this is the fastest synthesis of that molecule. Could you have made the alkyne in other places going backwards? And the answer is yes. It just takes longer. What you have to watch out for is you have to watch out if you're trying to do an SN2 reaction on this compound right here. your synthesis will not work. Okay, that's all I have for this follow-up. So